Okay, we're going to start. You can take your seats, please. So it's my pleasure to introduce our guest speaker today, Michał Farniak. He's come all the way from the University of Warsaw in Poland to tell us about some very exciting work that they've been doing in farm engineering. I won't attempt to describe exactly what you're going to talk about. And my co-host, I guess, is Professor Gabriel Santa Maria, who has just recently joined the Colorado School of Mines. He's working with us on various projects. So, did you want to say anything more about Michał? We are very impressed with how young Michał is and how much he's done.
Thank you for the introduction and for the invitation. It's my big pleasure to be here. And I'm enjoying Colorado a lot. So
Can you hear?
I could also get the microphone, but I think I prefer to speak loud. Okay. No, it's fine. Yeah, it's fine. So okay. It's a big room.
It's a big room and the dogs are absorbed.
The trick is to put it such that it doesn't make noises. Okay. Perfect. So I'm gonna tell you about our work in Warsaw in the Center for Quantum Technologies, which is a unit devoted to exploring some applications of quantum optics. So my background is from has been from experimental physics all along. So I did my PhD in the same school, so the University of Warsaw, and I already then started working with cold atoms. So I'm gonna really start because it's a big experiment that we've been doing, and I will start really with some stuff that I did during the PhD. In the meantime, I worked with Eugene Pauling in Copenhagen on quantum mechanics as well as hot vapor magnetometers and worked on enabling membranes with atoms. And then since 2021, I've been starting up a new lab in Warsaw. So I continue working with the cold atom experiment, which I'm going to talk about today. And then we also use rare atoms as a new topic that we started up for quantum sensing and transduction. But before I dive into that, I want to introduce our idea for using the optical quantum memories. So the optical quantum memory is for us an atomic medium that can store light in a way with a precision up to a single photon. So in a perfect scenario, it will be able to store an external single photon and retrieve it as a still a pure single photon state. And that should also work for many other kinds of states, like for example, coherent states or squeezed states of light. And the way we store information in the atoms is in the coherence of the atomic medium, which we call spin waves. So this spin wave storage is really one idea to use the memory. However, our idea is that we can also use those memories for other applications, which is not only storage but also generation and many kinds of optical signal processing. So photon generation is indeed one thing that I will show, but more distinctively, we have also devised protocols in which we can interfere light, which is being stored in the memory in a controllable fashion. So this really connects largely with many ways you can multiplex such memories. So in telecommunications, it's certainly popular conjugate variables for us. And since those atomic ensembles are spatially extant, we can also store light in many spatial modes, either by sending photons one by another or sending them at different angles. So the long-term applications of using those memories can be quantum repeaters, since it is since in telecommunications you can always just amplify your optical signal, but if you want to send single photons, then amplification inadvertently brings noise, and you need more tricky protocols that I will not be discussing in detail, but in general, those memories are a way to do it. And if you implement such complex protocols, then indeed it is good that your memory can do some at least basic signal processing, because you may want to implement error correction. And those error correction protocols, they in the most advanced scenarios, they really should implement kinds of quantum gates, either based on linear or nonlinear optics. So this is the kind of long-term outlook. But now diving into the operations of the memory. So it is to understand how we make the generation and or storage of single photon, we really need to consider a single atom. So the atomic ensemble will be able to store many photons more efficiently. But if we look at the structure of a single atom, then we need two states which are long-lived. So assuming we put an atom in the H state, it's going to remain there for a while. So to interface those two states, if you want them to be long-lived, then they, in our case, in the case of rubidium atoms, they are pretty close by. So they are separated in energy by 6.8 gigahertz, which is the hyperfine split. And if we want to make a storage of light, then we also want to interface to some optical transition. And for that, we need an excited state. So we will be running two photon transitions between the state G and H. And one example of such a transition is that we apply an off-resonant laser beam, which generates the so-called two-mode squeeze state. So a two-mode squeeze state, in a certain approximation, is really a generation of a pair, and more conventionally, people have been generating pairs of photons. So each photon of a given energy can be easily split into two photons, each with a half energy. However, here we are not generating directly pairs of photons. Instead, we generate a pair of photon, which is denoted by the orange dash line, and a single atomic excitation. So this is then called that we created a two-mode squeeze state between atoms and an optical field with the orange dash line. And then this atomic excitation is stored in the quantum memory in the form of a spin wave. And this so-called spin wave is really a collective quantum state of those atoms. So if we generated only one photon, then it is really only one atom that got excited. However, actually we don't know which one or which atom of this atomic ensemble got excited. So the spin wave state is really a superposition of one atom being excited, but we don't know which one is excited. And the phase factors, those e to I k times r, where Ri is the position of this excited atom, encodes a certain spatial phase, and the spatial phase is here a plane wave with the wave vector k. So the wave vector is really the frequency of this spin wave, the spatial frequency. After such a storage, I will show that we can do storage that can last from nanoseconds to about 100 microseconds in those ensembles. However, if you want to aim to make very long-term storage, you can even go up to seconds. And this is not necessarily required. Sometimes you just want to do fast processing, and really, if you can do many microseconds of storage, that's just excellent. So after this storage, we do a retrieval process. So we apply another laser field that now scatters this excited atom back to this G state and generates a photon. And this photon is pretty much perfectly correlated in both the emission angle and the nature of this quantum state with the first scattered photon. So we often call it that this is a Raman interface. It really reminds what it happens in Raman spectroscopy. And those photons, we either like to call them Stokes and anti-Stokes, but you can also think them as the write out photon and the read out photon. So we didn't really write any external information here. If you wanted to write an external photon, you would actually only use this process. And then if you apply a field here, then you will coherently transfer this atom to H state. So in a way, storage of external light is a bit simpler. So now, in about 2017, we implemented this protocol in our cold atom setup. And our new thing that we introduced was to really take advantage of the multiplexing of emission angles of those photons. So since this atomic ensemble has a spatial extent, then we can apply this writing beam and to get scattered Stokes photons in many simultaneous directions. If we then apply a readout beam, then we get those anti-Stokes photons that are now correlated with the Stokes photons. We can get them read out in a slightly different direction, so they're well separated. In practice, we can even make them have a different wavelength. So practically, they are well separated. And that gave us an idea to create a device that can quasi-deterministically generate single photons or maybe even multi-photons. So the idea is the following. If we just apply this write-out beam and we run the process of Raman scattering, then we get some random scattering events. If we only had a single mode, so we just put this photon into a single mode optical fiber, then it is a stochastic process. Then we will actually quite rarely get a single photon. Sometimes we'll get two photons. And if we get two photons, then it's pretty hard to detect. If it was really two photons, you need to consider losses and everything. So it's not really a great source of single photons because if you want to avoid generating multi-excitations, which are hard to detect, then you need to keep your generation probability low. So you will get single photons at the readout stage. However, you will get them rarely. On the other hand, if you are using many modes, then you can keep a low probability of generation of a single photon per each of these modes, where you could imagine that those could be single mode fibers. So you can keep a low probability per single mode, while having a near unit probability of having a photon in any of those modes, just one, for example. So the answer is, well, you just need a lot of modes, but that's actually not that hard. So now, if you would be able to detect these Stokes photons, then you can mark their positions. So you need a camera that can detect single photons, and then feed forward the positions and reconfigure some active photonic switching component such that the photons can be arranged. So here an example, we could rearrange those 4 photons into 4 specific modes. So the modes in which those photons get emitted at the readout stage are no longer random. We only need to apply this feed forward in a way that we compensate the random positions of the scattering events. So to implement it, here are 2 difficult things. except for the quantum memory itself, a camera and an active switch. And we've been able to solve one of those challenges. So for the camera, we have constructed a device out of several commercially available components, which can nicely see single photons. And now it can also generate signals for the feed forward in a time that's shorter than the memory lifetime. So such a camera is starts with the so-called image intensifier. It is a vacuum tube technology where you get a photocathode, a microchannel plate, which is really a electron multiplier, which keeps the spatial resolution thanks to having many microchannels. And then those electron avalanches hit a phosphor screen, which is used for detection. So it's somewhat challenging to detect those electrons directly. So instead, we opted for having optical detection. So while this photon was really a single photon, here, where those electrons from an avalanche hit a phosphor screen, they really induce a bright flash of the chemical that's in the phosphor screen, which is already actually a green light, not infrared. And this can be detected using a conventional camera. So on the camera here, you will see, of course, you use a grayscale camera, and you see those flashes. Their amplitudes are stochastic because the electron avalanches vary. However, you can mark their positions using software and then see correlations, as here as an example, between the Stokes and anti-Stokes photons. And in our work, we've been able to show for the first time that indeed those correlations have such a large scale. So we have in the past moved single optical fibers to see that indeed, yes, there is a correlation of emission angles, but we've been really able to look at the two output ports, the Stokes and anti-Stokes, and if we then marked the positions of registered photons, we saw that indeed they are very correlated. And you can also devise a measure to see if such correlation would be classically allowed and not coming from a quantum scattering process. And we've been able to prove that those correlations are indeed quantum and not classical. So more recently, we have upgraded the camera part of our device. So the image intensifier is really still the same thing, gated using our custom high voltage driver. However, more work we have put into the camera. So instead of using a commercial CMOS camera, we took a very fast sensor. Fast sensor in this case has a small disadvantage that it is more noisy, but it is really fast. It can do up to hundreds of thousands frames per second. And having such a fast sensor hooked up with our custom FPGA circuit, we've been able to show that we can get a delay between registering a photon and actually having the information about the photon's position to about 10, 20 microseconds, which is already faster than the memory lifetime. So if we could now direct this information to the switching element in a reasonable time, for example, such a switching element could be an acousto-optic modulator, then we could implement the protocol fully and obtain a really big advantage in generation of multi-photon states using this quasi-deterministic protocol. So this is often called that the quantum memory here is used for the synchronization of those independent modes. And if you compare this with the unsynchronized single photon source, which even rise at a much higher repetition rate, this is what people often do with femtosecond lasers, then we can still have a big advantage in the generation of multi-photon states, especially if we go to generating many photons. This is our story of the spatial multiplexing. However, the memory can also support other kinds of modalities. We found one of the most conventional and useful ones being the temporal multiplexing. So, in essence, we want to send a train of defined pulses of light into the memory and retrieve the same kind of train of pulses. In practice, it will be reversed in time, but that can be also changed. And we will actually be concentrating on sending a train of pulses, try to do some manipulations in the memory, and only then doing the retrieval. So the idea for putting the multiplexing in those kinds of memories was really sparked by a work from a group in Australia who decided to put the atoms in a gradient of magnetic field. So I'm giving this example since this is a very similar system to ours. And what they did is when you put those atoms in the magnetic field, you get a splitting of those two levels, G and H, that now starts to vary as a function of the position along this cloud of atoms. Here they actually use the vapor cell, but it works in a similar way for a cloud of atoms. And how I like to understand that is, so this is called a gradient echo memory protocol. So if you put your information in a gradient of a magnetic field, this is really not bad for the phases of this information, because now the evolution, the evolution of those coherences between states G and H will vary in the position, and they will actually get dephased very quickly. So the idea is to actually indeed dephase this information and then switch the gradient of the magnetic field for and have a rephasing. So then only if the rephasing is perfect, we will be able to retrieve these pulses. So another way to understand it, which I like a lot, is that now if we have this different splittings along the cloud, then different frequencies of light are mapped into different positions along the atomic ensemble. So, for example, if the signal has a smaller frequency, it will be mapped at the beginning of the atomic ensemble, and if it's a higher frequency, then it will be mapped at the end of the atomic ensemble. So we clearly have a spectral resolution. And given that the spectrum and time are related by a Fourier transform, then that gives us immediately also a temporal resolution. So how, in practice, how we operate the protocol is we can store one pulse, and if we apply the continuously apply the gradient of the magnetic field, the coherence associated, the spin rate associated with the pulse will actually obtain a wave vector. So it will obtain some momentum, kind of just slides on the gradient of the magnetic field. So then we can actually apply several more pulses, and only after some time we can perform a retrieval. So we put the same laser field, and we can retrieve a pulse. After switching the gradient of the magnetic field back to the opposite sign, we can select which of those pulses we retrieve. So here we kind of decided just to retrieve not all of them, but a specific pulse, but they could all be retrieved very easily, especially easily in a reversed order. So this indeed gives us temporal multiplexing for pulses, but we haven't really done any processing. Although you could think that applying those magnetic fields while the light is stored in the memory is already a process. So given that thought, we thought that to have more processing capabilities than just a linear gradient, we want something that can be more easily shaped than a magnetic field. It's not easy to probably have a big collection of coils to try to shape this magnetic field. Instead, we use an additional laser. So we look at this atomic ensemble. So this is our cloud of atoms, and we put a laser shaped using a spatial light modulator to the side of the atomic ensemble. And given that we can use the spatial light modulator from the laser just as an LCD screen, then we can apply absolutely any pattern, at least in the 2 out of the 3 dimensions, uh, onto the atomic ensemble. And because this laser shifts the atomic levels using the so-called AC Stark effect, then we can apply arbitrary modulations. So one example that we did is really implemented the same kind of gradient economy protocol. So we applied this AC Stark phases. We didn't want to apply a linear gradient, because if you apply a linear gradient of the intensity, then at some point you just reach a very high intensity and you need a lot of laser power. So instead, we apply a pattern which is really triangles in the intensity. That doesn't shift the wave vector of our spin wave. Instead, it splits it in 2. So it becomes a superposition of 2 different spatial frequencies. And then we can store another pulse and do that again, and store another pulse, and then in a similar way rephase those pulses using a reversed pattern and retrieve them in any order. However, now this is not all, because we can also implement a beam splitter inside the memory. So we apply one pattern, we store 2 pulses, but now we apply this modulation pattern only with half of the power. That actually leads to interference between the pulse that entered into the memory first and second. And we can retrieve those pulses in order. Here is an example data where the 2 pulses entered into the memory separated by a few microseconds, and then the 2 output ports are actually 2 beam splitter ports. So if we change the phase of this interference, we get fringes, which is the hallmark of a beam splitter. So this is the beam splitter operation that we did, but here we are still only using the kind of modulated linear phases. And then we thought really the one step further is trying to use quadratic phases. So if you apply a quadratic phase onto an optical signal, either in time or in frequency, that starts to look really like very conventional optics in the spatial domain. So a lens in the spatial optics really applies in the first approximation a quadratic phase in space to the optical. Furthermore, if you just let the beam propagate through free space, that actually applies a quadratic phase, but in the reciprocal space of the transverse wave vectors. So if we are now able to apply quadratic phases in time and frequency, that really starts to remind conventional optics, and that's why this entire domain is called often temporal imaging. So we can do imaging operations, but in the time frequency domain. So as you may suspect, we apply the spectral quadratic phase using our AC Stark modulation. And furthermore, it is actually pretty easy to apply the temporal quadratic phase. You can just use an acousto-optic modulator or an electro-optic modulator, which can translate voltages into the phase of light. An example to how to demonstrate such that we have this temporal imaging setup operational is to try to make a temporal analog of the Young's experiment, where we send 2 pulses in time, and we expect that after our temporal imaging setup, which will implement, in a way, a Fourier transform of the initial field. So we will look into what we would do in the conventional optics. You would take a lens and look far away in the focal plane, and you expect a fringe pattern. So people have been doing that mostly with ultrafast optics. So in ultrafast optics, you can get dispersion in a fiber medium or using gratings or prisms, which actually implements a quadratic spectral phase. On the other hand, to make quadratic temporal phases, it's a bit challenging. You can use some wave mixing processes or very fast electro-optic modulators. Our domain is clearly very different. It is easy for us to do temporal phases because our pulses are just slow, so we don't need any fast modulators. On the other hand, we need a very precise spectral control. And this is achieved using our AC circuit. And again, the trick here is that if you would just apply an intensity of the laser that grows quadratically in space, then at some point you would get a huge intensity, so you need a lot of laser power. The trick is to apply this phase until it gets to 2 pi, where it stops mattering whether it's 2 pi or 0, and then we just apply this spectral phase modulo of 2 pi. So this is what this is an example pattern that gets illuminated, or that gets sent and illuminates the atomic ensemble. So we also like to think about those manipulations in terms of the Wigner function. So you may know that in quantum optics, the Wigner function is very often used to describe quantum states. You take them in quadratures. So you have the quadratures of the optical field, and sometimes people study, for example, non-Gaussian states, and then one of the indicators of non-classicality is the negativity of the Wigner function. On the other hand, I know that in engineering, people often use these Wigner functions just to study the structure and the coherence of a certain pulse, for example, with radar science. And our usage of Wigner function is actually way closer to that. So we use a Wigner function as per this definition, where the A is the amplitude of the optical pulse, to try to understand how this pulse is being manipulated in the time frequency space. So in this case, we start with 2 pulses. So this is the Wigner function of 2 pulses, where the blue signifies that we have the 2 pulses, and the fringe pattern in the middle signifies that they are coherent. So when you try to see what is the intensity profile here, you just integrate over the omega direction, the frequency direction, and obviously you don't see the fringe pattern here. You don't see the coherence if you just measure the intensity. Now our quadratic phases that we implement in our protocol actually shear this Wigner function in different directions, and we apply 3 different operations, which are 2 temporal phases and 1 spectral phase. And after this full manipulation, we actually just rotate this Wigner function. And now if you integrate over the omega direction, so you measure again a pulse in the time domain, you recover the fringes. So this is really what happens there. And in our experiment, we did both ways. So we sent either 2 pulses or a train of pulses, which is the same as the fringe pattern. And then we either recover the fringe pattern here in time. This is measured using a time resolving photon counter, or we just recover the 2 pulses from a train of pulses. And more recently, actually, a very nice experiment done by some students that joined my lab very recently is that they also measured arbitrary angle rotations of those Wigner functions. So they took a fully map the Wigner function that you obtain after this entire operation, and they showed that you can rotate this Wigner function up to an almost arbitrary angle. It turns out the closer the angle is to actually the pi rotation, then it actually becomes way harder. And this operation, the fractional Fourier transform in this case, because it's not the full rotation, is also it has nice properties because the eigenfunctions of this transform are the Hermite Gaussian modes, and the eigenvalues are actually proportional to both the order, the angle of this transformation, the rotation angle, and to the number n of the Hermite Gaussian mode. So we've been able to show both in terms of amplitude and phase that indeed we nicely transform the Hermite Gaussian modes. So as the final application of our signal processing, we have turned back to conventional spectroscopy. And in spectroscopy, when you just want to resolve two close by spectral lines, which are incoherent with each other, so let's just say they come from independent emitters, then you are bound to be limited by the Rayleigh criterion. And the Rayleigh criterion is really well known in imaging, but actually it comes originally even from spectroscopy. And that's why also we looked into that and whether we can do something here. And beating this Rayleigh criterion can be a way to improve the resolution of your spectrometer. So the conventional Rayleigh criterion doesn't really consider the fact that if you have those two separated spectral lines, then in principle, if you would just measure for a very long time, then even if they are separated way less than the line width, like they have a tiny separation, then you will actually be able to say that, okay, but actually what I see on my spectrometer is like broadened by 1.5%. And that means that actually the lines are separated by a little bit. So they are not resolved, but you can still estimate the separation. And now, informationally speaking, a nice way to see how much can we know about this separation is the Fisher information. So the Fisher information is a way to measure how much a certain probability distribution, which for us will be a probability of getting a photon of the spectrometer matrix, is susceptible to a parameter theta. And you can use this Fisher information to derive the limit for the precision of estimating this parameter. And here our parameter is the separation between the two lines. And this limit is called the Cramer-Rao bound. And in the case of just using a spectrometer, you get an unfavorable scaling. So you can see that the information, the Fisher information about the separation scales quadratically with this small parameter. For small epsilon, it will be really horrible. So now it turned out that this is not really the limit. So it was discovered first theoretically by Mankei Zhang that if you consider all possible quantum measurements that you can do on this photonic state, then your scaling of the Fisher information, so-called quantum Fisher information, is actually constant. So you get 1 instead of epsilon squared over 8. It's like way more. And an example to implement this information, such a protocol, try to get it, is to consider that a spectral line shifted away from the center can be rewritten as the unshifted spectral line, unshifted Gaussian, plus a small contribution of a Hermite Gaussian mode. So if we try to measure only these contributions of the Hermite Gaussian modes, then we will get a background free information about this separation. An example to do that has been called sliver, which is an abbreviation for inversion interferometry. So image inversion interferometry. So you want to take in the spatial domain, you take the image of your source, you split it on a beam splitter, you invert the image in the x-axis, and you interfere it back. And one of the ports, if the phases of the interferometer are correct, will contain the information about the spectrum separation. And the Fisher information for that is constant only with a small correction. So it's almost a perfect protocol. So in our case, we first used our quantum memory to just do the conventional protocol. It's actually already quite interesting because since those atoms have a high coherence time and we can control the states precisely, then we can implement effectively a spectrometer for those two spectral lines, which we generate using acousto-optic setup. But interestingly, I mean, it already has a resolution of 20 kilohertz. So it is a very high resolution in terms of an optical field. So, but clearly it is limited by this Rayleigh criterion. So to beat that, we implemented an idea based on what I've shown previously. But now we do not reverse our pulse in the spatial domain, but we have to reverse it in the temporal domain. Fortunately, as I have indicated, our memory can do that. So you remember that we had the trains of pulses, and after the retrieval, we were able to see that they often get retrieved in an exactly reversed order. So if we do that, but only for a part of our pulse, then we can reverse a part of our pulse and interfere it back. And then the two outputs in the time domain, separated by a few microseconds of our memory, are really proportional. One of them becomes proportional to epsilon without any background. And we've been able to show that indeed the inverse resolution or the Fisher information we get for each photon emitted from our simulated source indeed carries more information than the Rayleigh limited approach. So this may be a slightly weird thing because we've just implemented a very precise spectrometer that still requires to use atoms. And those atoms only work with some wavelengths. You can use frequency conversion to adapt to do that wavelength. But I believe that this really mostly gives a nice idea how to also try to implement it in other systems. On the other hand, many optical systems do emit very narrow band states of light where it could be useful to interface them with the atomic media. For example, I have myself worked with optomechanical systems that have about 10 kilohertz line width of the emitted radiation. So it is actually compatible with our setup. But indeed, we have just explored a regime in terms of the line width of our source, which is in the kind of kilohertz level, rather the conventionally explored terahertz level. So one other example of a similar protocol was implemented in Paderborn, and this is called a quantum pulse gate, where you can also project onto this Hermite Gaussian pulse. So we have achieved a similar level of quantum enhancement, however, in a very different regime. So before I briefly move to the Rydberg atoms, I want to show one other funny experiment that we did. So since we are able to implement beam splitters in the memory, we can also replicate one of the very famous experiments in physics, which is called the Hong-Mandel effect. So in the Hong-Mandel effect, you send two identical photons on a beam splitter, and if they are really identical, so they must be the same wavelength, the same polarization, and they must arrive at the same moment at the beam splitter, then they will just stick together. So if you write out the contributions to this interference, then the events in which the photons exit from another port actually just cancel out in an equation. So if you put a coincidence counter at the output, you get 0 coincidences if the photons are identical. And we've been able to show the same effect for our photons, but stored inside the quantum memory. So we implemented this splitter inside the quantum memory and shown that indeed we reduced the number of coincidences by 80%. Therefore, showing a way that even though most of our processing methods were implemented using very weak but coherent states of light, then we believe that our memory can also be useful for quantum states of light, with obviously some enhancements needed to improve efficiency and possibly repetition. Okay, so let me jump to the topic of using our atoms for quantum sensing and transduction between microwave and optical fields. So it is one of the big long-term goals to be able to communicate superconducting circuits which operate at microwave frequencies using optics. And for that, we need a transducer which can take a single microwave photon and convert it into a single optical photon, one way and the other. So this is a very high-end goal because we don't want to add any photons of noise, and we probably want an almost 100% efficiency. So using our atoms, which even are laser cooled, they sit in room temperature, or they just not even laser cooled, they sit in one of those vapor cells. We certainly wouldn't be able to immediately do that because we have a room temperature environment. So instead, we started thinking, can we use this transduction properties of the atoms for more near-term goals, like, for example, being able to receive very weak microwave signals and upconvert them to the optical domain to use, for example, optical photon counting detectors. And that's how also we got in touch with Gabriel here, because he worked quite intensively on the topic of trying to show where this can be applied. And we know that this reception of weak microwave signals is not really the only application of the atomic media. You can also use atomic media, for example, for imaging. So I want to highlight one work where they had used actually even an incoherent process, which is in a way even more impressive, to image terahertz light using Rydberg atoms and the fluorescence that they emit. So other approaches to quantum transduction are very intensively explored. So you will see that the system that I've shown can also do some transduction using not going to those very difficult to reach Rydberg levels. So you could use a microwave transition in rubidium that's 6.8 gigahertz between two ground state levels. Unfortunately, this is a magnetic dipole transition, so it has a very poor dipole moment. The coupling is pretty weak. Now, one of the very big domains is quantum optoelectromechanics. I have worked a little bit on this optomechanics, which I'll mention. The topic was pioneered also here in Boulder, and the idea is to use a LC circuit for the microwave, which can also couple to light via making the capacitor of this LC circuit mechanically coupled to an optical cavity. So while this can be implemented in a plethora of ways, then this joint coupling makes the mechanics being a mediator between optics and microwave. You can also be a bit more direct and use electro-optic materials or use magnetic effects in a field called optomagnetics. So we'll be looking at using atoms as this transduction medium, and this has been explored a little bit. So last year, one group has shown that you can use such a process in an atomic ensemble. So you go to those high-lying Rydberg levels, and you can absorb a microwave here and emit an optical photon here. This is a six-wave mixing process, so you need several optical and microwave fields to drive it. So they have achieved actually quite nice efficiencies of the transaction without any considerations for noise as of yet. However, as has been published this year, you can, in a slightly different process, which is, so the kind of the process is a bit of a technicality, because here, again, the group of John Simon, who moved to Stanford now, has been able to absorb a microwave photon, 100 gigahertz, and convert it into a photon at 780. And both of those photons live in cavities. So one is a high finesse optical cavity, and the other one is a superconducting microwave cavity. So those experiments actually achieve not only high efficiency, but also very low noise, because this entire atomic ensemble now lives also in a cryostat, a very advanced experiment. So before diving into our approach, I want to highlight the work that was done in Copenhagen. So I have myself worked with just optomechanics. So we've been putting those silicon nitride membranes that couple to light via reflecting a little bit of it into cryogenic assemblies and studying how they interact with light. A group next door of Professor Albert Schließer has also put bits of superconductor onto those membranes and try to simultaneously couple them to both optics and microwaves. So it's an ongoing effort. But we go on with the Rydberg atoms. So the Rydberg atoms are a really nice medium to sense microwaves. One example for sensing the microwaves, one of the big advantages is that you are able to see the amplitude of the microwave sensed by the atoms directly in the spectrum of those atoms when you try to do a laser spectroscopy. So if you apply the microwave between two states of the atom, those two Rydberg states, then if there are any atoms there that don't decay too fast, then you will get the so-called Rabi oscillation. The frequency of the Rabi oscillation, which is the population oscillation between population as well as coherence oscillations between the two states, is proportional to the dipole moment and the amplitude of the electric field of the microwave that we are applying here. So we are applying this microwave here between those two Rydberg states, and to actually reach them, we use a probe beam and a coupling laser. So this is at infrared, and this is actually a blue light. And then when we don't apply the microwave, we see only a single transparency peak. This is called electromagnetically induced transparency. This is induced by this coupling laser. But if we apply the microwave, it gets split in two by the amount proportional to the amplitude of this electric field. And here is one of the early examples, early demonstrations of this splitting. And now people are working on many practical protocols that employ this effect. For example, you can put some microwave circuits like a coplanar waveguide here inside the chamber with atoms and sense the field very near the surface of this waveguide. And you can think of having really miniaturized sensors. For example, I want to show that in Copenhagen, we actually haven't worked with the Rydberg atoms, but we've been, my colleagues have been developing a magnetometer system that's all optically coupled because it's supposed to go into an MRI machine. So people here at NIST also work on all glass sensors with Rydberg atoms, and I think it's a very interesting application to have an all optically interfaced sensor. So our approach so far is humans that work on that. Our approach so far is to use a different kind of a six-way mixing process to convert a microwave into a signal photon. And while this is quite similar to the demonstrations before, it has several practical advantages that allowed us to make it work with a very simple system, a room temperature vapor. So in this case, we are emitting light, which is at 776 nanometers, which is quite far from any different other wavelength present in the system. And that allows us to make a very easy filtration, optical filtration, so we can use quite conventional optical elements like dichroic mirrors and interference filters to filter out almost any noise. Furthermore, unlike the very advanced experiment from the team of John Simon, we do not use the UV laser. This UV laser severely limits the duty cycle of those experiments because it is very damaging. You need a lot of power, and it is quite damaging to optics. So you can read in the paper that they cannot shine through the cavity mirrors for more than a few microseconds because the mirrors start to burn away pretty much. So here we don't have any crazy wavelengths, and the system is actually pretty simple. So we direct all those lasers into a single vapor cell, and we get our signal at 776 using several dichroic mirrors out into the optical fiber. So our microwave is generated using PLL synthesizer, while our lasers are locked to a reference laser. So we use a fiber laser, which is very narrow band, about 100 hertz line width, which is used as a reference, and we use cavities. So each of these optical cavities is locked to the reference laser, and then each of those lasers, which have completely different wavelengths, can be locked to the cavity. Since we want to avoid metal elements, we want the atoms to be evaporated in the cell to a reasonable vapor pressure. We found out that it's beneficial to heat them up a little bit, and we developed a 3D printed casing for the cell, which heats up the atoms a little bit using air channels. So the hot air is inside the 3D print, therefore it also doesn't disturb the optical beams. Now, for detection, we can use different methods. So most of the time, we've been using superconducting nanowire detectors, which are very sensitive. They have very low dark count rates, which is beneficial. But we can also use a heterodyne detector by obtaining a local oscillator from a completely separate laser. So it's not going to be perfectly stable. That's the problem, but it can allow us to analyze the emitted signal. So we first observe our signal in a pretty strong regime. So we put a lot of microwaves, and we scan the frequency of one of the lasers. We found some optimal parameters for the emission of this conversion signal, which is so we were actually very surprised that it is optimally not emitted at the same frequency as this conventional EIT effect. And to understand the atomic structure, we have also scanned many different lasers. This is what you want to do if you want to understand what those lasers are really doing to the atom. So now for the result, our setup works kind of over a wide range of regimes. So it's if you apply a lot of power, then actually your output rate starts decreasing. We can predict it. This is due to saturation. So the microwaves are splitting the levels of the atom so much that the protocol doesn't really work. However, this splitting can be used, as I previously suggested, to calibrate the intensity of the microwaves and therefore the absolute voltage, because we can calculate the dipole. Now, if we decrease the power of the microwaves, at some point we just hit a noise floor. And the question is, what is this noise floor? And our work has really been concentrated around proving that this noise floor is not a technical noise of our setup, but rather the thermal noise of the environment that we are up converting to the optical domain and detecting using our photon counting detectors. So uh, first of all, we've been able to show that indeed the noise density, the voltage noise density of this thermal field indeed matches the theoretical prediction for the noise floor, matches the calibrated intensity from this outward down split. So to provide this theoretical prediction, we went back a little bit to the basics about what is the amplitude of the noise, of the thermal noise, and we provided some corrections for the fact that our medium doesn't convert the microwave radiation isotropically. Instead, it acts, in fact, as an antenna with some gain. And for a physicist, this is actually called, because for us it's a wave mixing process. Therefore, in optics, you always call it that this is phase matching. And phase matching often means that you need very specific refractive indices of your medium, such that all the momenta of photons that you are trying to add and subtract add up finally in the entire process to zero, and then the process is phase matched. And this is the same here. So the phase matching in this medium leads to the fact that it acts as an antenna. And for the sigma plus polarization, so we use circularly polarized microwaves. This was adjusted for the sigma plus polarization. It has it can collect radiation from about 90-degree angle, and the sigma minus polarization is almost negligible here, but we also take it into account. So this is one thing. This is our prediction for the noise density. If we want to see how many photons we really convert, we also need the bandwidth of the conversion. So we can't really directly see the bandwidth of the converted radiation, but in such a small range, around 14 gigahertz, the thermal radiation is really a white noise. So what we can do is just apply a coherent microwave, scan it across the conversion bandwidth, and this is the red curve. So we get about 17 megahertz. And this is enough really for us to give what is our bandwidth of the converter. But as an added trick, we can also adjust the frequency of one of those lasers to extend this conversion bandwidth. So this is an example of trying to use this entire laser setup for our advantage and have a broader conversion bandwidth, although it's not instantaneous, so you need to adjust one laser. And now this conversion bandwidth is also nicely related to the coherence properties of the thermal field that we have. So if we take S of omega as our conversion bandwidth recovered from this measurement, we can also have the first order coherence of our thermal field, which is also nicely related to the second order coherence. Oh, right. So here I also want to directly show the tunability of our converter such that we can tune the microwave. And normally, if we just tune it, it will be this much of a bandwidth. But if we adjust one of the lasers, we effectively extend the bandwidth of the converter with some, of course, decreasing efficiency. But you can always say that the full width at half maximum bandwidth is indeed extended. So if we use this heterodyne measurement, then we, for a coherently converted microwave, then we see that the line width of the conversion is about 80 kilohertz, while our microwave is really narrowband, certainly less than 1 hertz line width. And this is because all those lasers introduce some phase noise to the conversion process. And to resolve it, we will soon be resolving to nonlinear optics. But I will skip that since this is a whole another story. Instead, as far as the photon counting is concerned, then there is one interesting way to see the coherence of the thermal field, and this is just to put the photon, those thermal photons, upconverted photons, on a beam splitter and look at the coincidences between two outputs. And thermal radiation has this property that it gets bunched, and the bunching, the characteristic time for this bunching is related by a Fourier transform to the bandwidth of the radiation. So if we have 17 megahertz, then we expect some 50 nanoseconds of bunching characteristic time. So we were very happy when we first saw from our time tagging device some peak in this correlation. So this is really normalized number of coincidences. So we measured longer and we got a very prominent result already. And the shape of this bunching peak corresponds really well to the theoretical prediction of this coherence from the bandwidth measurement in the previous experiment. So now we decided to play some tricks with that. So if you not only apply a thermal radiation, which is just there, but also an off-resonant coherent microwave that gets converted simultaneously, then you will get a bit node between those two, and this is those bit node fringes in the coincidences. And in general, if you apply this coherent field at the same frequency, then the more coherent field you apply, the less of the coincidences you get, because a coherent field has is just purely the photon counts are purely random, so you get no bunching of any kind. And as the very final proof that we are indeed looking at the thermal radiation, we did probably the simplest thing possible. So we just covered using a black piece of paper all our lasers and all combinations. So since there are several lasers driving the process, this is actually several combinations. You also want to cover some pairs and all three, almost nothing. And from this entire measurement, we concluded that most of the noise that is still in the process comes from only one of those lasers. We've been able to later eliminate that, and this is the C laser, the coupling, the blue laser, and this is actually a very technical piece of noise. It's just that the blue laser, as photons have high energy, so they induce a little bit of fluorescence in the glass of the optical setup, especially in the very vapor cell that the atoms are sitting in. And we, even though this fluorescence is isotropic, it goes in all directions, a little bit of it goes into our fiber, and this is our noise. However, this noise is at least 50 times lower than the thermal radiation, the upconverted thermal radiation that we observe. So we hope to move this experiment away from being a free space atomic antenna to be a cavity enhanced, where you can use an external antenna to couple a signal. And this is not an easy feat, but the atomic process that we explored, we believe, is quite well adjusted for that task. So in a way, our dark noise in the process, the added noise not due to the thermal phonons, we like to say that it corresponds to the noise temperature of only a few Kelvin. And, while this is not exactly comparable with amplifiers, because we're not really amplifying anything here, and this is still can be very useful, because that means that as far as the added noise is concerned, this is negligible for the room temperature. However, we'll be also looking at other applications. We think one interesting applications would be to convert convert microwaves or a bit higher energies, about maybe 100 gigahertz, would be useful for that application using a spatial resolution. So we have our single photon camera. We can also do homodyne detection using cameras and try to observe converted fields with spatial resolution. So I hope I convinced you that this device has, for a room temperature operation, it has a low added noise. And compared with more complex setups, it can run continuously, continuous wave operation with a very good bandwidth. And as the final outlook, we've been also looking at implementing this in cold atoms. So recently we published a paper where we imprint some phase using this AC Stark laser onto our cold atom ensemble and are able to retrieve it. So here is, for example, the QOT University of Warsaw being imprinted onto our atomic ensemble. And we've also been able to show that those atoms are sensitive to a magnetic field, and we can recover it with a spatial resolution using only a camera. So this is a little bit similar to taking every slice of the atomic ensemble independently, but without really any movement involved, a bit similar to MRI. But since this is a sensitive method, then we also hope this can be applied to Rydberg atoms, for example, to sense a single Rydberg atom using another Rydberg atoms that would surround it. So thank you for the attention, and thanks for the team. So Sebastian is a first year PhD student. He just finished now, so he did the transducer experiment, and we have some senior people who worked on the cold atom for quite some years already. Thank you. Right. Yeah, it's a very rough idea for now. It's a good question. So yeah, if I am able to couple the cavity mode, so an empty cavity will have some line width, and this will contain the thermal radiation. But now one interesting thing to explore is whether I could read out the thermal photons faster than they leak into the cavity. So then I could maybe do even radiation cooling of the cavity. I think that would be really cool. I'm not sure if we can do more than 1 Kelvin of cooling, but that would be very interesting. And on the other hand, then you can think of engineering the external coupling, and then you will start seeing if you can do the external coupling be larger than the internal losses, then you will see some combination with the major factor of the external source. So you had coherent versus applied. Yeah. Is it possible that heat detection would be more sensitive into that aspect? Because obviously right, yeah. That's an interesting point. I don't know. Because I mean, it's a second order method. So it's not intrinsically sensitive because you need to wait for 2 photons to come to your detector. So it's like efficiency squared. So that's better. Sometimes those methods are good at detecting something small if you have a long time. Yeah, interesting. No. So there are several. To say that the photon pairs are non-classical, the most proper thing is so-called Cauchy-Schwarz inequality, where you do the cross correlation and also autocorrelation of each of those photons. And we checked that, and those autocorrelations were really small, which is what you need anyway. Now, to have a single photon statistics, then there is also a heralded correlation that you need to check. However, now they are quite related. So, as far as I remember, if you have thermal states and the G2 larger than 8, then your single photons will already be properly non-classical in the highest likelihood. So we've been above that, but we didn't collect the data for checking the real single photons in this case because we didn't have uh, the, the feed forward yet.
So you did the paradigm right, where you showed the time.
Yeah.
So could you also, because now you have the time domains, you also record the time domains and, and, and see what the statistics of that zero mean value noise signal is, and that know that it's actually if it's Gaussian distributed,
Right.
have the same bandwidth.
Yeah, so this 80 kilohertz, this is for a coherent microwave. So if you only have a thermal, so the advantage of looking at those thermal photons with photon counters is really the lack of background. If you use heterodyne homodyne detection, then you're getting shot noise, and this shot noise is a problem. So the question is, so this 80 kilohertz, it may be a problem, maybe not, but if you want to just detect thermal radiation, then your main problem is going to be that it's with our setup that is the free space, the thermal radiation will be way smaller than shot noise. It's an interesting question whether there you could.
So if the efficiency was 1.
If the efficiency is 1, it would be large. Yeah.
So could you use that as a proxy for efficiency? Like the threshold?
I think so. Yeah.
So we could
Yeah, in this case, yeah. So I agree. Although we can already use, we have a way to compensate for this 80 kilohertz, which should help a little bit, and then try to see a little bit of this thermal noise on top of the shot noise. Yeah, it's a small contribution. Yes. Yeah.
Thank you. Super interesting. Definitely. But I was wondering, so you said that it's easy to, make these spectral domain quadratic phase.
Yeah.
Is that sort of just linear group plane? How do you make those sort of?
Yeah. So in ultrafast optics, it's easy. It's indeed the group delay dispersion. So the larger if you have your light that's, I don't know, 10 nanometers, then you almost just take a piece of fiber and it has large dispersion naturally, unless it's exactly at, 12. There is like an O band around 1300 nanometers where there is zero dispersion. So you probably don't want to be there. You go anywhere else, you get lots of dispersion. To get yeah. So it's pretty easy. However, people also use methods a bit similar to ours to get larger dispersion, and they are called chirped fiber Bragg gratings, where you take a long but way shorter fiber and imprint a Bragg grating that reflects low frequency at the beginning and high frequency at the end. And yeah. Okay. So yeah, I imagine this must be also
Any other couple, again, not in my field, but I'm very interested in your processing, your first part of the
Yeah.
talk. When you mentioned the change of the gradient of the magnetic
Yeah.
field that you're reading and writing,
Right.
how big is that gradient?
Oh, that's a great question. So we designed around it a little bit. So we have so the range of the gradient is such that we get kind of megahertz level splittings per centimeter. So that's so a megahertz is so that's about a Gauss per centimeter gradient. And how we do that is we take almost anti-helpful coils. They have only a few windings of a thick wire, so they don't have too high impedance. And we take an array of N MOSFET transistors coupled with some transit diodes. So they induce about 150 volts in those coils. So we switch about 20 amps in 10 microseconds. And the high voltage comes from an additional kind of storage coil. So we have like a big coil, and that gets kind of shorted together. Yeah, it's an H bridge. The transistors are in H bridge. So this is our custom circuit actually. It's not something that you get immediately because it needs to be both high voltage and high current.
Yeah, so when you do that, then you set to read out, you change the direction.
Yeah, we change the
And
direction.
does it matter how fast that happens? Because you have a big current step, so you
Yeah.
can't change it too fast. You have a lot of time.
Yeah. So
It may not matter.
yeah, it must be faster than you don't want to. The atoms will decohere slowly. You want to be faster than that. We can do that in a few microseconds.
Cool. That's really interesting. Oh, okay. Yeah, no. You, iron engineer with glasses.
I believe maybe not electrically small, but I have seen like cells being put between plates or in a piece of a resonator, right? I'm not sure the name of that. Like a piece of wire and cut it. Yeah, split ring resonator. Yeah.
You could go again.
Right. So if you, I like to compare here with. So let's just say that we want to do storage of optical light, and how would we do that classically? In a way, a classical memory for light is a photodetector and then some generator of light. So if you take a very strong coherent state, like a strong laser, then you can most likely reproduce this state with a high fidelity. However, whenever you go to the level of single photons, whether it's coherent states or some fancy quantum states like true single photons, where it's just only one, then such a setup cannot do that for you. So you will not reproduce the same quantum state. And if a setup can really do that, then it is called an optical quantum memory, that it can preserve the quantum states at the single photon level. There are also some high intensity states, like for example, you can have so-called squeezed states that are actually squeezed light is injected in the LIGO interferometer, where it's actually a high intensity non-classical state. So in this way, actually, like it would be very hard to do that in this kind of memory, but like as another example of an optical state of an optical field that cannot be reproduced by just detecting that and trying to reproduce it.
So reminded by that gradient echo problem. When
Yeah.
you the magnetic zero, you lose the interference from like Majorana losses or something like that, or is that not an issue?
Oh, the zero field.
Yeah.
Yeah, we have a bias field. It would be the zero field is very problematic because then it's never really. If it was zero, that would be fine. But if you have like but around zero of z field, you would get some transverse components that they would just rotate the state in some random direction. So bias field helps a lot.
In another direction, right?
No, in the same direction. We do the bias field in the z direction. So we have like.
Does it flip that to a full negative?
No, it only flips the gradient.
Okay.
Yeah.
Got it. Okay.
We bias this to the one way. Good point, because we tried without the bias and it's bad. It works, but badly, like there are distortions to the losses. It becomes super sensitive to the external.
I was curious. When you did this was on the reverse. You took that the polarization of the incident wave was circular, and I was curious why.
So
Yeah, there.
so in this calculation, this is really just a decomposition. So
Okay,
we could,
totally.
it's two orthogonal ones. But in our experiment, in practice, we actually have a circular. We have like a helical antenna that makes it.
Are you in the near field or in the far?
Unfortunately, somewhere in between. Like it's.
So you don't know.
So so what we did is several simple tests to see. So this to have the perfect polarization here is not crucial, but we did several tests that show that it is actually pretty circular. So for example, we can try to reverse the polarizations of all the lasers and see how much of the other state is generated. And in intensity, it was about 100 times less. So it's a
Very good.
it was a surprisingly good query.
Oh, that's good. And you just lounge around.
Yeah. So on a 3D print, and then we took it away. They are broad. Yeah, that actually helps because we don't want to do very specific matching, although it was adjusted.
Great. Any other questions? Okay.
Okay.
Very good. Well, let's take questions.
Thank you.
This is awesome. So much fun.
Thank you.
Just
I'm
wish
gonna
I
stop the
understood.
recording.
Yeah.
It's a great time. To take off.
You go. Don't worry.
I'll be back later. Okay.
Don't worry. Where are you? Where do you know where